Just like to say first off to everybody, welcome to AVSO's webinar series. So my name is Brian Kloppenberg. I'm the executive director of the AVSO, and it's a great to see you all here today. And today we're going to be talking about, Rob always has really fun titles, and so it's about Pandora's Box. It's about how NASA and citizen scientists help avert disaster. And I haven't got a preview of his talk, so I'm very interested to see exactly what's coming in there. But before we get over to Rob's talk, I want to do a couple little introductions. So for those of you that have never been to an AVSO webinar before, or you haven't used Zoom before, just like to introduce you to a couple of controls that you have on your screen. So if you wiggle your mouse over the screen here, you should see a box that pops up at the bottom that looks like what's here. Please, if you would, use the chat feature to introduce yourself or, to have conversations with other folks during the webinars. If you do have any questions, though, please use the Q&A box. That'll be a little dialogue that you can pop up your questions, and it makes it a lot easier for Rob and I to be able to see them and answer them at some point later within the webinar. And Rob has indicated that he's probably going to take questions at the very end of the webinar in today's. And then if any of you need closed captions, there's also the closed captions button. Go ahead and click that and you pick the language that's actually being spoken. So in this case, it would be English. I'd also like to say a thank you to our series sponsor. I'd like to express my gratitude to Voice Astro, who has actually sponsored the entire 2025 webinar series. If you haven't heard about them before, Voice Astro provides online astronomy education, observatory resources, and research experiences to students and schools to perform observations, conduct research, and publish their results. So please check out their website over at voiceastro.org and learn more about their offerings in astrometry, photometry, and spectroscopy. I'd also like to mention that the AVSO is a 501c3 nonprofit organization. Everything that we do is actually being supported either by our endowment or by the generosity of other individuals that are out there. We receive virtually no federal funding, and so I very much appreciate it if you would consider supporting the AVSO by scanning the QR code here or visiting avso.org/donate now. All donations made to the AVSO are, of course, tax deductible within the United States. And without further ado, I'd like to introduce Dr. Rob Zellam, a frequent visitor on the AVSO's webinar series. I think the 3 years that I've been here, Rob, you've given a talk every single year. We're incredibly grateful for that. Without further ado, here's Rob.
And despite that, you keep on inviting me back, Brian, even though
You're
you
always a
should
lot of
know
fun,
better.
Rob. Yeah.
Well, thanks again for having me. Thanks everyone for calling in. Seeing lots of friendly names on the line, such as Bob Massey and Pat Boyce, Andre Kovacs. Thanks everyone for calling in, for supporting today. Really appreciate it. So I'm Rob. I work at NASA's Goddard Space Flight Center. That's in central Maryland, just like half an hour northeast of Washington, D.C., on the east coast of the United States of America. And I'm really honored to be part of Pandora's science team. So Pandora is a small sat mission that'll be looking at exoplanets and really trying to disentangle activity on their host star from polluting the signal of the exoplanet and causing a false positive on the exoplanet's signal as well. Before I talk about Pandora, though, let's just talk about some background first on exoplanets. So there's a variety of different ways that we can use to find exoplanets: so the radial velocity, the transit, the direct imaging method, gravitational microlensing, timing, astrometry. But the one that Pandora will be leveraging is something called the transit method. So those of you who are involved in Exoplanet Watch, just getting a little bit of a review for y'all. But if you're not, the transit method is extremely helpful because it enables us to measure the size of a planet and also to measure and characterize the atmosphere of the planet orbiting around its host star. So let's say we're observing a star. We're really lucky there's a planet orbiting around that star. And if we're even luckier, the geometry is just right, where that planet will occasionally pass in front of the star and it'll block out a portion of the star's light and cause the star to appear to dim. And this effectively, this dip in brightness tells us the area of the planet relative to its host star. So we can actually back out, if we know the radius of the star, we can then understand and know the radius of the exoplanet. This is a really, really powerful method. What's also even more interesting, in my own opinion, as someone that's very biased and uses this method all the time, is this method enables us to study an exoplanet's atmosphere. So when we observe a planet passing in front of a background star, not only does the optically thick portion of the planet absorb the star's light, but also the thin annulus of atmosphere also transmits and absorbs and scatters and blocks some of that background star's light. So if we compare what the star looks like without a planet in front and compare it to what the planet does look like in front of it, we can take the difference of those two and see what the planet signal looks like alone. And from that, we can actually, by looking at the spectral signature, how the planet absorbs and scatters light as a function of wavelengths, this will tell us what molecules and elements are in the planet's atmosphere. So again, the transit method is extremely important because transits enable us to not only measure the radius, the size of these planets, but also they enable us to study a planet's atmosphere. So missions like Hubble, like James Webb, have all been using this method to characterize transiting exoplanet atmospheres. This method has also been used very successfully to discover 4,000 of the currently known 6,000 exoplanets to date. And at best, this is about a dip in brightness of about 1%. The one mission you probably have heard of, and I know a bunch of you are involved in, such as Bob Massey as well, is NASA's TESS mission. This is the Transiting Exoplanet Survey Satellite. This is a picture of TESS at the center of the screen. It's doing this full sky survey, and it's doing that with these 4 digital cameras. Now, it'll take slices and it'll slew around the entire sky. And over the course of a few months, I'll map out one hemisphere at a time. And TESS is predicted to discover tens, if not hundreds of thousands of new exoplanets. And the reason we care about that is because, again, we know about 6,000 today, so we know a lot already. But TESS will give us even more targets that we can then follow up with future transiting exoplanet survey or characterization missions. So Hubble Space Telescope, top left, that's observed about 50 exoplanets, probably a bit more now, and has looked at their transmission spectrum to analyze the light being absorbed by the planet's spectrum, by the planet's atmosphere, and then we can back out what molecules, what elements are in that planet's atmosphere. The James Webb Space Telescope completely revolutionized the field. This is a 6.5 meter telescope compared to Hubble's 2.4 meter telescope. James Webb not only has a more massive mirror, but also has a whole slew of instrumentation that expands our wavelength coverage beyond what Hubble previously or is currently doing for us. Hubble covers the ultraviolet to the near infrared. James Webb covers the long wavelength in the visible, but really the near infrared out to the mid infrared as well. And these wavelengths are important because these correspond to where molecules most strongly absorb and emit light. So James Webb, not only from its giant mirror, gets us more precision, but its increased wavelength coverage gets us access to more wavelengths of light. And from that, we can access more molecules as well. So this is one of the reasons why when James Webb was first launched in December 2021 on Christmas Day, why almost every single observation coming out of James Webb is revolutionary and very pressworthy, because we've never had this sensitivity, we never had this wavelength coverage before. Looking ahead now to the future, we have the NASA's Pandora mission. This is a small set that I'll be talking about today. Then we have the Roman Space Telescope. This is NASA's next flagship mission. I also am very privileged to work on at NASA Goddard. We are launching that no later than May of 2027, or perhaps as early as October of 2026. The Roman might be launching next year. Roman will be discovering hundreds of thousands of new transiting exoplanets. And then a little bit farther into the future, the European Space Agency, ESA, is launching a mission called Ariel. This is a dedicated exoplanet mission that'll be launching roughly around the end of this decade, so just in about 5 years from now. And Ariel will be doing spectroscopy on up to 1,000 transiting exoplanets. So this gives us finally a statistically significant basis of what we can look at when we're looking at planets. Hubble and James Webb have been giving us tens, maybe hundreds at a time. Ariel will give us 1,000 planets, at least hundreds of planets. that we can put those Hubble and James Webb observations into a larger statistical context. So we can say things like, how common our hot Jupiter is, or how common is methane in an exoplanetary atmosphere. We can answer that question with error. And then looking beyond that, NASA's Habitable Worlds Observatory. This is NASA's next flagship mission. It's in pre-phase A, so we're literally designing it right now. This will be launching in about 15 years from now. And HabWorlds is at least a James Webb size mirror or larger, about 6.5 meters across. It'll also go to L2 like James Webb. But what's super exciting for me as an exoplanetary scientist and a giant nerd, you can't see my home office right here is my Star Wars poster. Happy Eve of Star Wars Day, everyone, by the way. HabWorlds is explicitly designed to look for Earth-like planets around sun-like stars and look for signs of life, to look for biosignatures that indicate that life exists on the surface of these planets. So right now, we're truly in a golden age of exoplanetary science, and I'm very honored and privileged to be part of this. I remember when Hubble was doing transformative science when it launched in about 35 years ago, I think last week. And now we have all these different missions that are coming up, and all of them are really enabling and helping push forward the field of exoplanet science. All right. So all these missions will be using likely, if not certainly, the transit method to look at exoplanets and to characterize their atmospheres. But let's talk more about Pandora, which is why I'm here today. So Pandora is what's called a small sat. This is part of a recent call by NASA. It's a new phase of NASA. Typically, NASA has done larger space telescopes. So Pandora is a smaller funding class, so it's a bit cheaper, and they're faster missions. They don't take quite as long to develop and to launch. It's about 0.5 meter telescope diameter. It has only a 1 year prime mission, but in that year, we'll be observing over 20 known exoplanets to look at their atmospheres, but also to measure their host stars. I'll talk about why this is so important in a second. Pandora's wavelengths are from 5 to 2.4 microns. This is the visible and the near infrared. These are the same wavelengths that we're using on Hubble and on James Webb to characterize exoplanetary atmospheres. And we will be in a sun-synchronous low Earth orbit. So sort of similar to Hubble, but we'll be mostly orbiting around the terminator of the Earth. So we have less cut-up periods where the Earth gets into the way. And we are ready to launch in fall of 2025. And last I heard, about a week or two ago, we will be hopefully launching October of 2025 of this year off of a rideshare option at Vandenberg Space Flight Center. And that's in the central part of California, just north of LA by a few hours. All right, so this is getting back to how we conduct and observe planetary atmospheres. So when we observe a transiting exoplanet, if we observe that at various wavelengths, we can actually measure how the planet's radius changes over those various wavelengths. The reason the planet might look bigger or smaller at different wavelengths is because it might have a molecule in its atmosphere that is more or less efficient at blocking out light at those wavelengths. So for example, if I am observing, say 2.3 microns, I think is like CO, if I'm remembering correctly. Just to pretend it is so I don't lose face here. If a planet has lots of carbon monoxide in its atmosphere, that will cause the atmosphere to look more opaque or larger at those wavelengths. If I look off of that absorption band of carbon monoxide, for example, at 2.1 microns, the planet might look a little bit smaller. So the planet actually, its radius varies as a function of wavelength. And if we can then translate that radius variation with wavelengths, we can then actually back out what molecules are doing that absorption. So this planet is very efficient at scattering or absorbing or blocking out light at 2.3 microns. It's not as great at 1.8 or 2.1 microns. There must be some sort of molecule in the atmosphere of that planet that's blocking out the light of its host star. And from that, we can actually figure out what molecules are in that planet's atmosphere. But when we're observing transits, we're always doing differential measurements. We're always measuring the planet relative to its host star. And when we're doing these measurements, we're hoping and we're assuming that the chord of light, the area that the planet blocks out, is indicative to the rest of the star. But y'all online know that stars are active, star spots are localized. So if a planet transits a chord of light that doesn't have activity and it's compared to an active part of the star, that can mess up our math because we're always measuring flux of the planet relative to flux of the star. So if the flux of the star is different than what we're expecting, that will alter the flux of the star, the planet, the signal of the planet, and it will pollute the signal of the planet. And it can actually cause false positives. So let's look at a simulation that I did eons ago. Good Lord, about 10 years ago now. What I'm showing at the top is the spectrum of a host star with an exoplanet transiting around it. So the planet's orbiting around the star, and we have the star spectrum. This is also over the Hubble WIFC-3 passband from 1.1 to 1.7 microns. At the time that I did this simulation, Hubble was still the only and the best, in my opinion, method of observing exoplanetary atmospheres. So I made this figure for that. At the top is the spectrum of the host star. In the green dash line is an unspotted star, so a star that's not active, and it's boring in that sense. The red solid line is a star with about 3% star spots on its surface. And then the blue points are simulated Hubble data, Hubble observations of this star spectrum. In the middle panel, right down here, this is the change in the stellar spectrum due to spots. So how much does the star spectrum change between unspotted and 3% spots? And you can see there's this sort of gradual change that's more pronounced at shorter wavelengths versus longer wavelengths due to star spots. And this is due because star spots are typically cooler than their host star. Therefore, they have a different black body signature. They have a different spectral signature than the unspotted surface of their host star. And due to the temperature of these spots, we see this effect more pronounced at shorter wavelengths towards the visible or the near infrared. So here, the change in the stellar spectrum due to spots is about 0.5% different. And at longer wavelengths, it's more or less not as much change. It's less affected by these star spots. Now, down below, if you look at how much the planet's signal changes due to spots. So again, if the star changes from what we expect, if it has spots or plages or faculae, if it has bright spots, cool spots, relative to what the unspotted surface of the star is, it looks different or changes from what we expect. That actually can alter the retrieved spectrum or signature of the planet itself. That can very vastly change what we expect to observe on the planet as well. So right here, this is the unspotted star spectrum. And here's the planet spectrum with that 3% spotted star. So if you look on the left on the y-axis, it's a very small change, admittedly. It's 0.015%. But if you compare that to the precision on a typical Hubble data set, that actually starts to get into something that's more statistically significant, like 3 to 5 sigma. So the change in the signal is 3 to 5 times larger than the size of the uncertainties. So those are statistically significant changes. Luckily with Hubble, it really hasn't had the precision where this truly matters. We could more or less mostly sweep this underneath the rug and not worry about it with Hubble. However, thanks to James Webb, we have a new era of astronomy. James Webb, thanks to its larger mirror, about 3 times larger in radius and diameter, enables higher precision. So these error bars here on this plot have now shrunk. And that means that this change in the star from unspotted to spotted, or the planetary spectrum between unspotted to spotted, has now appreciably changed. And now the community is really worried about this, rightly so, this effect, and how we can mitigate this effect and remove it so that when we're measuring the planet, we're truly measuring the planet and not the star polluting the signal. So let's look at some real data. Here in white is actual James Webb data of an exoplanet called GJ486b. This is I believe, a super Neptune planet around a solar type star. If we were to then model the atmosphere of this exoplanet, the data in white, we can actually fit it with two different models. We can either fit it with a blue, water-rich atmospheric model, or we could also fit it with a star spot model alone. And the reason why this happens is because the star spots are so much cooler than their host star in some cases, where water can actually start to be observed and it's not no longer photodissociated. So some of these star spots are actually cool enough where you can actually see gaseous water vapor in the spots. And that can masquerade as water in the planetary spectrum. And that's actually right here. So 1.1 to 1.7 microns. This bump right here is actually the telltale spectral signature of water. So you can either fit that with a water-rich atmospheric model right here, which then also fits these data points out here. Or you can just purely get an atmospheric, a lack of atmosphere on this planet and just purely fit it with star spots that can mask or mimic that water spectral feature here and here. So stellar contamination masks or mimics the detection of water in exoplanet atmosphere. And perhaps this can do it for other molecules as well. And actually, stellar activity can actually induce us to think that a planet might have hazes in its atmosphere, when it actually might have a clear atmosphere. So this can really change and alter our interpretation of the exoplanet's signature. So we need some way of removing the polluting signal of a star from that of the planet. And that's where Pandora comes into play. Pandora will be observing these star spots, these active stars, about 20 planets or more across the visible and the near infrared. And we'll be looking and pointing Pandora at stars that we know have stellar activity. And Pandora will be doing a bunch of different things. They'll be observing these planets in a snapshot of time, about 24 hours, but we'll also repeatedly come back to these stars and these planets, see how the planetary spectrum has changed over time. So the animation on the bottom left is you see an active star that has lots of coronal mass ejection events or faculae, and the star will be brighter and dimmer over time as star spots rotate in and out of view. And we have this faculae rotating in and out of view, and CME events rotating in and out of view. So when we observe the planet at this phase or this phase, where the planet is brighter or the star is brighter or dimmer, that could potentially impact and change the planetary spectrum due to this epoch to epoch variability, because stars change over time. And then with this animation, we're looking here at a super Neptune planet observing around a transiting a star, and we can look at the transmission spectrum here, just like I talked about before, to figure out what sort of molecules are in that planet's atmosphere and confirm that they're actually coming from the planet and not from the star itself. And again, Pandora will be in the visible 0.5 microns to near infrared, about 2.3 microns. And we chose that wavelength specifically in the visible as well, because it really gives us overlap with James Webb. James Webb also covered about 0.7 microns to, I think, about 9 to 10 to 15 microns in the infrared. So we'll have a nice overlap there of James Webb. But we really wanted Pandora to have that visible wavelength coverage as well, because it enables us to really explore the degeneracies of these model fits. So again, here's the James Webb data in white. Here's our star spot model that's about to pop up in orange. And then here's our pure atmospheric model of the exoplanet in blue. And while they look very similar in the infrared between about 1 micron and 5, you can see they diverge here at shorter wavelengths, about 0.5 microns towards the visible. So perhaps we have something at these wavelengths, they can help us break that degeneracy. They can tell us if that star is active or not, or if we're observing the planet, or if we're truly observing the star. So visible wavelength ranges, photometry spectroscopy are crucial I would argue, to helping us figure out if it's the signal is coming from the planet or from the star itself. So that's just due to latent activity on the host star's surface. But these host stars, as I mentioned before, can also change over time. Just like our own sun has solar minimums and solar maximums, these stars also go through periodic variability changes as well. So this is a bit of a busy plot, I totally admit, but most of this data is coming from two papers um, where they have observed the activity of an exoplanet's host star called GJ1214b. GJ1214 is the host star. That's an M-dwarf type star, very active host star. And you can see that the blue dashed line, the green dashed line, the red dashed line, and then the solid fuchsia line or magenta line, those are all different activity cycles observed in the I band and the V band of the star over a couple of years. So those are all fits to historic data. So what this is really showing is how much the star has changed over just about 2 to 3 years of observing it. The blue data points are data that we've extracted from the Hubble Space Telescope. So in the infrared between 2012 and 2013, it kind of fits some of the same data. So what this plot really shows is how the star can look different, not only as a function of time, but also as a function of wavelength. So we really need to observe these stars across wavelengths. We also need to observe these stars as a function of time. And ideally, we also want coverage when things like Hubble or James Webb are observing them as well, so we can better analyze these host stars and make sure that their signal is not leaking to the signal of the exoplanet. So that's honestly, that's the most driving factor behind Pandora here. So Pandora, again, that small sat that'll be launching hopefully this October, will be observing 20 known exoplanets. It'll be observing each of them 10 times over 24 hours each, spread out across a year. The reason that we've adopted this cycle, excuse me, is hopefully so we can measure the full rotation rate of a star over about 24 hours, or at least a good portion of the star's rotation rate over those 24 hours. And we come to it over a year to observe it at different parts of the activity cycle. So we're modeling here by looking at the star's light between 0.5 and 2.4 microns. We'll be able to observe, for example, how the change in the star spectrum induces change on the planetary spectrum as well. And from that, we can monitor the host star spot fraction. We can measure how the spot changes affect the star spectrum. We can isolate exoplanet atmospheric signal, and we can also detect water in these planetary atmospheres and hazes as well. And we truly need a dedicated mission for this. We can't just use James Webb for this because this is a full year of observations from a single dedicated exoplanet mission that's done much more cheaply than James Webb. So I have to crunch the numbers, but I think one of the main driving factors behind this is that Pandora can do the science that can help enable and unlock and help us better interpret and increase the scientific output from Hubble and James Webb and future space observatories by Pandora, a relatively cheaper model. But as I mentioned here on the slide, Pandora's prime mission lifetime is about a year. We're hoping that we'll get an extended mission and Pandora will last at least one more year longer, if not even longer than that. But we only have at face value this guaranteed 1 year of observing time. So sort of taking this into account, we were figuring out ways where we could enhance the science return from Pandora. Perhaps we can start observing Pandora's targets today from the ground using small ground-based telescopes to extend the baseline of the observations of Pandora using folks such as yourself. And this is where small telescopes can definitely help. There are 3 plots that I published back in 2020. Good Lord, that's 5 years ago now. My God. On the left, this is the scatter. On the y-axis, the uncertainty of looking at a star versus magnitude. So brighter stars on the right, you get smaller uncertainties. Dimmer stars are on the left, you get higher uncertainties. And this is all data taken of the Micro Observatory, a 6-inch robotic telescope built about 30, 35 years ago that's still operating today out in Tucson, Arizona. And by looking at the Micro Observatory telescope um, and their data, we were able to very quickly figure out that you can get really high precision data and observations with even a relatively old compared to commercial telescopes that are available off the shelf today, from a telescope that's robotically controlled outside of Tucson, up to about 0.5% per minute of a host star. That's extremely high precision, only over a minute of time. To expand this to half an hour or an hour, you can even greatly decrease those uncertainties. Um, what we've also found is that not only can these small telescopes can help us achieve high precision observations of the host star, they can also enable us to achieve high precision observations of the transiting planet as well. And when you observe a transiting planet, you're actually getting a 2-for-1. You're not only observing the light of the star, you're also observing the light of the planet blocking, or really the planet's disk blocking out the star's light as well. So you're observing both a planet and a star in these observations. And we found really quickly that small telescopes like the Micro Observatory, even smaller telescopes, can do high precision observations. We can look at transit depths of these planets uh, down to a fraction of a percent with a single 6-inch telescope. And we can also measure their transit times very accurately as well, on the order of a few seconds, if not a few minutes. And this is extremely important for many reasons. For Pandora, what this enables us to do is observe ahead of time these transiting exoplanets, and then we can more accurately predict when a transit event were to happen. So this enables us to schedule Pandora more efficiently and effectively, and to make sure, for example, when we're downlinking data from Pandora down to the Earth, to the ground, that we're not doing that downlink and turning away from the transit when the transit event is happening. Because some of these planets have minutes uncertainty of their transit events. This also helps out missions like Hubble and James Webb, because by observing these transit events with a small telescope, we can update the times of when these transits have occurred and use that to more efficiently and more accurately estimate when the next transit were to occur. They can better predict when the next transit were to occur, and therefore we can do a more efficient use of James Webb and Hubble time and other space telescopes to then observe that target again in the future. So we can use these telescopes more efficiently and hopefully increase their science output. And this is the whole reason behind why we launched Exoplanet Watch about 6 or 7 years ago. It's really this citizen science project to leverage all the amazing work that folks, amateur astronomers, citizen scientists, people of the AAVSO have been doing for years, to really sort of tie in that expertise that all of you have been doing and have you directly help us out with Pandora, with Ariel, with Hubble, with James Webb, to routinely observe these transiting exoplanets to keep their transit times precise. And by doing so, you are directly helping enable NASA science, and you are a crucial part of this, as I'll talk about a little bit later as well. So Exoplanet Watch, we're a collaborative effort to complement existing surveys. We're very honored to have this amazing relationship we have with the American Association of Variable Star Observers. We utilize all the time their exoplanet transit database, where they host all the observers' data that we scrape every other day right now. Also, the variable star catalog, the star charts, the field of view plots, everything. It's been such a great uh, boon to our project by working with the amazing folks at the AVSO. So really, really appreciative for all the work that they and all of you do as well. All of our data is immediately public. There's no proprietary phase to our project. You can go on our website right now. You can download any data from any transiting exoplanet or star. You can write your own papers. You can scoop us as well. Just we ask that you cite our paper, you give us acknowledgement, and also if you publish data from an observer that has never been published before, you invite them to be a co-author on your paper. And this is something we are very passionate about, that observers are listed as co-authors on papers. Because quite honestly, if you do the work, you deserve the credit. And we've already, and just by, I think we've been really had our public launch for about 2 years now, maybe 3 years at this point. We've already had tens of our observers, of our citizen scientists on 10 to 15 to 20 published papers just by taking their telescope and pointing at a transit, or by using data curated by us from the microobservatory, um, and using that data and analyzing it and contributing directly to NASA science. We also have target requests by professional observers and as professional astronomers. So, for example, we have this amazing partnership with Pandora. This is actually why I was asked to join the Pandora science team, was as the project lead and project scientist at Exoplanet Watch. They wanted to get all of your help, and they were looking for me to organize and coordinate all this together. So I'm very honored and lucky to be working with amazing people like you and helping out Pandora as well. And we're very fortunate to be funded by NASA's Universal Learning. So as the Citizen Science Project, we have both science goals and educational goals. Our science goals are really our low-hanging fruit here is to ensure the efficient use of large telescopes by updating the future transit times. We are also monitoring for stellar variability, as I'll talk about a little bit later in a second as well. And that's really to expand that observational baseline of Pandora. We're also starting to get into the discovery and confirmation game. So Super Corley, one of my students, is on the line. Thank you, Super, for calling in on a Saturday. Really appreciate that. Super and some of our other students at Arizona State University are working right now on discovering new exoplanets using small telescopes. I know a lot of you have also been involved in the TESS mission and the TFOP, TESS Follow-up Project mission. So Bob Massey, for example, you're observing test candidates and you're helping NASA and TESS confirm and validate these planetary candidates to confirm that they are real planets as well. But as a citizen science project, we also have these educational goals to engage and teach the public about exoplanets and enable them to do science, and hopefully to really inspire the next generation of folks, kids in high school, in college, to become professional astronomers or join the STEM field to become future leaders for astronomy. And we're actually very lucky to have a lot of student involvement in this project. So Super is an undergrad at ASU out in Phoenix, Arizona. We have other schools, high schools, and colleges across the United States and the world that are including Exoplanet Watch as part of their curriculum. Boyce Astra, for example, and Pat Boyce include Exoplanet Watch in part of their choice programming as well. So we're very, very honored that people are using Exoplanet Watch for part of their education and part of their labs. But then also some of those students are doing their own scientific studies and writing their own peer-reviewed scientific papers that they're then putting out there in the literature. The Calais Talk, for example, from Stanford Online High School, has had many students writing their own first author publications, their own peer-reviewed papers that are helping us to update these transit times. And some of them are now going to school to study astronomy at illustrious places such as MIT. So it's pretty awesome what's been happening in the last few years of Exoplanet Watch. So if you're interested in joining, here's the roadmap to participation. I'll step through this one at a time, so don't be overwhelmed. If you are lucky enough to have your own telescope, and if you live in a location that occasionally has clear skies, you can actually go on our website, plan your own observations with a plugin we use through the Swarthmore Transit Finder. And then just like Brian Martin there in that photo, you can use your own rig to help us observe transiting exoplanets. If you're like me and a federal employee who doesn't have enough money to purchase your own telescope, who is married to a historian, you're clearly not doing this for the money, folks. We love doing this. We're very honored to be able to get paid to do this for sure. I don't have my own telescope. So what I do and what some of our other users do, especially if you live in a cloudy location, you can actually check out data from us from the microobservatory. So we're very lucky that the microobservatory has donated over a decade's worth of data to us, thousands upon thousands of data sets. And we need your help to help us analyze this data, to go through it one at a time, to translate it, to analyze it, to reduce it from those raw images into a final transit light curve. So regardless of how you get your data, if you take it yourself or if you get it through us, through our data checkout system, you then analyze it yourself. You can use a variety of different methods that you want, for example. So, for example, Dennis Conti uses Actor Image J. I know a ton of you use it as well. A bunch of you might also participate in ExoClock, uh, effectively the European version of Exoplanet Watch. Love those folks. We collaborate with them all the time. They are really focusing on these planets and these ephemeral, these transit timing measurements for the Ariel mission, and we're really honored to work with them. They have their own tool called HOPS that lots of folks love as well. We have our own exoplanet transit tool called Exotic that I'll talk about in a second. So you get your data, you analyze it yourself, and then you upload it to the AAVSO's exoplanet transit database. Again, we are very lucky that the AAVSO is letting us use the transit database for this project. I remember when we were designing this project, trying to figure out how the heck we would get people to upload data to us and contribute to us. For some reason, NASA didn't want members of the general public uploading data to NASA servers. I don't know why. So this really made things so much easier. And we have thousands, if not tens of thousands of observations in the last 3 years, thanks to our amazing partnership with the AVSO. And then you sit back, relax, you publish your own papers, you get published. Again, you can go on our website and get any data products you want, as well to publish in your own studies. And some people have done that. I talked about those data analysis tools. One of them that we built specifically for a project is called Exotic. This is our exoplanet transit interpretation code. This is a real astronomy analysis tool. This is exactly what I do as a professional astronomer myself. It's literally the exact same code. The only difference is that the front end is a little bit more user-friendly than the Python Unix version that I use. So it's absolutely the same exact tools that are used by professional astronomers to analyze data. And this is to teach you how science is done. So you actually use the same tools I do as a professional astronomer. We have step-by-step tutorials on how to use Exotic online. And actually, a really cool thing about Exotic is you can actually run it on your smartphone or even your Chromebook laptop. You can actually run this completely on the Google Colab Cloud. So basically, you sign up for a free Google account. Most of you probably have a Gmail and already have this account. You effectively connect with a remote Google server or computer, and you run all the code on that server. So you don't have to install anything. You don't have to download anything at all to your computer. It really makes the data analysis portion a lot more streamlined. So there you get your data, you analyze with Exotic or HOPS or AIJ, whatever you want. As long as it's in the right format to upload to AVSO, we'll take it. And then you get published, or you can publish your own data. One observing campaign, which that I'm very proud of, is back in 2021, we observed a transiting exoplanet in support of James Webb observations. The problem for this is that the transit itself was over 12 hours long. And when you observe a transit, not only do you need to observe the in portion parts of the transit when the planet's passing in front of the star, causing the star to dim, you also need to observe before and after the transit. So we're looking easily at a 13, 14, 16-hour observation here. And literally anyone across the world, it was impossible for any single observer to observe this entire transit. So what we did is we activated our user base, and we had people across the entire globe, across the Northern Hemisphere, that all observed this transit throughout the night. So effectively, what we did is we simulated a single large telescope that spans the entire globe across the Northern Hemisphere. We had people in Eastern Asia and Japan and Central Asia that started observing the pre-transit baseline. We had people in Europe and the West Coast United States observe the transit. And then this person out here in teal observed it again at the end of the night, the very next night as well, and stitched all this data together. We had over 24 facilities, all relatively small telescopes, less than 0.7 meters or 30 inches across. A majority of our telescopes, though, were 2.4 inch telescopes, like the Unistellar EV scopes. So you don't need a large telescope to do impactful science that helps out missions like the James Webb Space Telescope. We had 24 facilities that I mentioned. We probably had another 20 to 30 that wanted to participate. But as is tradition, I am convinced that clouds are sentient and know when you're trying to observe or when you buy new gear, because most of the Northern Hemisphere was clouded out. We had a lot of folks in Western Europe and also the East Coast of the United States, for example, that wanted to participate in this campaign, but were completely clouded out. So this wide distributed network of telescopes got us two things. It enabled us to observe the entire transit, to simulate that single telescope spanning the entire globe, but it also enabled us to mitigate the impacts due to clouds and weather on the Earth's surface. One of my students is leading some observations of Pandora targets right now. This is Fred Nuger, also collaborates with Super Corley at ASU. And Fred is working with some students in the Philippines to remotely observe on a telescope out in Tucson, Arizona. This one's a little bit bigger than probably what most of y'all have at home. This is a 61-inch or a 1.5-meter telescope, hence the amazing data quality. But we're able to use this telescope out in Tucson to observe these Pandora targets and to go after ones that are dimmer or smaller transit depth, smaller signal than what we could achieve with smaller ground-based telescopes like a 6, 8, 12, 0.4, 0.6-meter telescope that an amateur astronomer might typically have in their backyard or remote observing site. So Fred is now going after the planets that are typically dimmer or shallower, smaller signal targets. And again, not only is he observing the transit when the planet passes in front of the star, he's also observing the unocculted, uncovered portion of the star's light as well. And from that, by observing these over multiple epochs, multiple times, nights, and months, we're able to piece together the variability of these stars. So here on the left, these are two different stars, and we're measuring the variability of the stars over time. These are from the Las Cumbres Observatory telescopes. I believe they're 0.4 meters and they're 1 meters across the globe. And what he does is he does an analysis on the data to look for periodic signals in the data. And then by doing this analysis, we can phase or combine the data together to look at how the data or the star varies in brightness over time. So for example, this one, you can see how we have that really nice wavy pattern as the star is brighter or dimmer due to stellar activity. This is likely tied to the rotation rate of the star itself. What we're likely observing here is a star spot rotating in and out of the field of view as the star rotates over a few nights. This is important because it allows us to measure the rotation rate of the host star. And this will enable us to then better interpret other exoplanet data, such as from Pandora or from Hubble or from James Webb. So if you're interested in joining Exoplanet Watch and directly helping out missions like Hubble, like James Webb and Pandora most immediately, you can get started here on the website, exoplanets.nasa.gov/exoplanet watch. You can also scan this QR code. I am terrible about memorizing URLs or QR codes. So if you just Google NASA Exoplanet Watch, we should be the first thing that pops up. Again, you don't need a telescope to participate. We have tons of data that we need your help to analyze. But if you are one of those amateur astronomers in the line that is lucky enough to have an amazing rig, as many of you folks of the AVSO typically do, we would really appreciate your time and your help and your effort in observing these transiting exoplanets to help us to expand the science capabilities of missions like Hubble, of James Webb, potentially of Roman in the future, but most immediately, the Pandora Small Sat mission I'll be launching this fall. With that, thank you so much for your time. Thank you so much for dialing in on a Saturday, and especially those who are late at night. And I'm happy to pause here and take any questions you might have. And Brian, I think we do that by looking at the chat, correct?
Yeah, you're welcome to go through the chat yourself if you'd like, or I can help as well.
Yeah, sure. Yeah. So, for example, Neil is saying how Hubble has one primary monolithic mirror, 2.4 meters. Roman does as well. The Roman Space Telescope also has a single 2.4-meter monolithic mirror. James Webb has a segmented mirror design. And that's great because it allows us to control each individual mirror surface to help get a more in-focused picture with the James Webb Space Telescope. Jack is asking, can amateurs contribute spectroscopy? yes, spectroscopy of these host stars is something that is extremely important as well. So for photometry, that gets us a passband of light or an average of light over a specific wavelength. With spectroscopy, we can actually look at how the light of the host star varies over those different wavelengths. And that's important because this allows us to actually start to look a little bit more in depth and get more information about the stars when you break it down by wavelength.
Hey,
So
Rob,
that is, yeah, go ahead.
just a small thing. It's actually the Q&A box, not the chat box.
Oh,
So that way we can see what questions have been answered versus what haven't. Um,
okay. Thanks, Bert.
no
Let me
worries.
get the Q and oh, there it is. Sorry, I clicked the wrong thing.
No, totally fine.
Oh, perfect. All
I
right.
just didn't want everyone
Yeah,
starting to ask their stuff and then forgetting about the other questions. So
yeah,
Perfect. All right. So make sure you ask in the Q&A box, not the chat box. Okay. So the first
yeah.
question I see, thank you,
Actually,
is
Rob, could I
go
could I
ahead.
follow up just a moment with your
Yeah, yeah,
your
please.
spectroscopy comment? So I've been working with the spectroscopy section over the last month or so to get them into a variety of different things, right? We've been starting
Mhm.
off with classic binary star orbits, but of course there's also a lot of people that are monitoring other things. In terms of exoplanets, is there anything specific that you would want, in terms of spectral resolution? Cadence, like what kind of data would you be looking for from amateur spectroscopy?
Yeah, that's a really great question. And honestly, there's not a single answer to that question, unfortunately, because the stars all have different rotation rates. So it kind of depends on the rotation rate of the star. But if you can get at least, one data set a night for about half an hour, perhaps, of spectroscopy, for example, that would be helpful. Or even photometry over that night. That way, you can look at how the star's spectrum or the star's photometric signal changes over time. So spectroscopy is extremely helpful. Photometry is extremely helpful as well. Does that answer your question, Brian?
Yeah, it does.
Yeah. So some folks also ask me, can you do spectroscopic transits with small ground-based telescopes? Unfortunately, the signals that we're looking for in these planets is way too small. The smallest telescope that I've ever used for spectral signatures, looking at spectral signatures of an exoplanet, is a 3.5 meter telescope. So if you happen to have a 3.5 meter telescope, awesome for you. Definitely get spectra. But most of you, I think, you'll be limited to looking at the host star itself. You
Okay.
could bin the data together to look at the broadband signature of the planet, but you're probably not going to be able to look at spectral signatures that will tell us about molecules in those planetary atmospheres, unfortunately.
Okay. So probably just looking at the broader photometric behavior of the star, and then any kind of bulk spectroscopic changes, or maybe even like the presence of either traditional star spots or like chemically spotted stars would be the
For
kind of
sure.
things you look for. Okay,
And that
perfect.
would be extremely helpful because there's
Yeah.
not a lot of groups actively doing this in the world. So we need your help. There's thousands of exoplanet transiting targets that we need to observe. There's only so many professional observatories. There's many more of you amateur astronomers than there are professional astronomers in the world. So we definitely need your help to do this work, this very crucial work. All right, I'm seeing in the Q&A box, how can we distinguish between planetary transits and false positives called by binary stars, star spots, or instrumental noise in light curves? That is a great question, and the bane of my existence sometimes is trying to figure out if a signal is coming from a planet or a star. For eclipsing binaries, you actually look for the eclipse when you have the smaller primary or the smaller secondary star passing from the primary. You can also observe when the secondary goes behind the primary, and that'll have a very different shape and signature than when a planet goes behind its star. So you can actually figure out that way by looking for an eclipsing binary. For star spots for sure can look like transiting exoplanet signals. That's why we look for repeat signals and repeat visits, 3, 5, 20 times if you can of an exoplanet transit, because those star spots vary with time. They change over time, whereas the transit should have that roughly that same shape over many different revisits as well. Instrument systematics, the same exact answer, honestly, is we look at repeat visits of these transits. And if you are lucky enough to have spectroscopic capabilities, you can also perhaps look at where these two data sets diverge here. Let's skip ahead to see if it's coming from the star or from the planet. All right, next question is, will Pandora use TRS or data transfer? And can you tell us how much data the system expected to generate? I forget, quite honestly, how much data will be generated by Pandora a day, but all the data will be immediately public for the community and any of you to download as well. I believe it will be hosted on IPACS servers and perhaps also MAS servers. So just the same places that you get Hubble data or James Webb data, you can also get Pandora data as well. Are there any opportunities for citizen scientists to help generate targets and update ephemerides for known systems? Yes, and that is one of the main bread and butter things that we're doing for Exoplanet Watch. So if you're interested in observing these planets, update their transit times so you can more efficiently use Pandora, Hubble, or James Webb, please do join Exoplanet Watch. We absolutely need your help. The next question is, how can we extract atmospheric composition information from transit data given the faint and subtle signals involved? And that's why, honestly, you need that bigger aperture of these missions. So Hubble 2.4 meters, the smallest telescope I've been able to use on the ground is a 3.5 meter instrument. You need these larger apertures to get the signal to noise, the precision that you need to look for these bumps and wiggles in the atmosphere of these signatures, these planets, to look for these shapes that are indicative of water absorption as well. So you need that larger aperture. Ideally, you also need spectroscopy as well to look at how the light of the planet varies over here with wavelength. Pat's asking what stellar classes represent the 20 stars. I believe, Pat, that we're mostly focusing on K and M, maybe some F and G types as well. So we're looking for stars that are known to be active. K and M dwarfs are more active than larger stars. And these are also very scientifically important because these smaller stars, the M dwarfs, for example, they will have a larger transit signal around them for a given planet size. So for example, if I take an Earth-sized planet and I put it around a sun-like star, that Earth is about, if I can do math off the top of my head, 100 square smaller in area than the star. So the signal is very, very small. It's about 0.01%, if not smaller, if I can do math on a Saturday afternoon, I'm sorry. If I take that same planet, an Earth-like planet, and I put it around a M dwarf, which is 10 times smaller than our own sun, that signal now approaches about 1%. So scientists, astronomers have been interested in observing M dwarf stars to look at Earth-sized planets simply because the signal is larger and easier to see. But unfortunately, those M dwarfs, like TRAPPIST-1, for example, are more active, and there's an open debate on if we're detecting the star or are we detecting the planet. Zahir is asking what are the magnitude range of stars observed by Pandora. All over the place. We're observing some stars, I think, as dim as 10th, 11th, 12th magnitude in the V band, and as bright as 8 to 9. Some of the Pandora targets are dimmer, but a lot of them can be directly accessed by amateur astronomy rigs, telescopes as small as 6 inches. And actually, we're observing them right now from our telescopes out in Southern California. We have a bunch of 6-inch celestrons, a 0.6 and a 0.4 meter telescope that almost every single night are observing a transiting planet for Pandora. The next question is what criteria to select the 20 stars for the observation? It's done by weighting and picking targets that we think that will be observed by James Webb, so we think, or Hubble. So targets that we think that are interesting targets that will be observed in the future or have been observed in the past, but also stars that have known stellar activity on them. So they have interesting spectral signatures, or they have the potential to have spectral signatures that are interesting to observe and can be observed, but they have this problem of having the stellar activity that we need to remove and correct for. The next question is, will there be Pandora targets in the Southern Hemisphere, and how will we know to observe and to measure? Yes, Pandora's targets span the entire sky, Northern and Southern Hemisphere as well. This is actually one of the reasons why we need your help, especially if you're in the Southern Hemisphere. Most of the Exoplanet Watch observers were in the Northern Hemisphere. We need folks in the South. This is why I've applied for time on telescopes Mauna Kea or lower altitudes, such as Las Cumbres Observatory, to get us access to Southern Hemisphere targets. We publish the Pandora targets on our website for Exoplanet Watch. So one way to do that is to join Exoplanet Watch and actually hop on our Slack channel, because there's a Pandora channel where you can directly get information on that too. But you can also Google the Pandora mission, NASA Pandora mission. Make sure you add NASA in there so you don't get jewelry or like a music app. Pandora, NASA, SmallSat. On the website are the Pandora targets as well. So everything is immediately public and open for anyone and everyone to grab. Oh, and Yogesh, this question is way out of my pay grade, unfortunately. They're asking how Pandora's all-aluminum 45-centimeter coated Cassegrain telescope design optimizes thermal and optical stability to achieve the high atomic precision needed for simultaneous visible and near-infrared exoplanet atmosphere characterization. Unfortunately, I do not work on this part of the mission, and I do not know how that works. So unfortunately, I cannot answer that question for you. But if you'd like to, I can try to ask one of my office mates when we get back to the office on Monday and hop on the Exoplanet Watch channel and our Slack, and I can ask for you and answer that question perhaps in a few days. Anonymous is asking, if cost is an issue, would you accept photometric data from a DSLR camera? Yes, for sure. Any data is useful. DSLRs are great. And you can plot them, like you've mentioned here, on equatorial mounts or on an off-the-shelf telescope, and you can do really incredible science with it. DSLR cameras have typically a Bayer array, so they require a little bit more inventive or more involved data analysis or reduction. But Unistellar's EV scopes, for example, use Bayer array cameras just like a normal DSLR would as well. So there are definitely ways to analyze the data to reduce it and contribute it to us for sure. But that being said, getting a dedicated monochrome camera, that could be in your best interest over time if you want to make higher scientific grade observations. But a DSLR, I always opt for people to start cheap and start easy, and then see if you like it or see if you run into any issues and then graduate from there. Don't spend money if you don't have to. Pat's asking for preferred visible wavelengths. Don't care, Pat, as long as you get us data, that's really what matters at the end of the day. A lot of people find that R-band observations get them the highest precision. I think that's what we do at Table Mountain out in LA. So whatever gets you high precision observations is great for us. If you have the capability to observe over multiple wavelengths, even better. So if you're able to take like 5 or 10 observations in R band and then switch over to V band and flip flop between different passbands, that's even better. Timothy is asking, by measuring the rotation rates of the stars, how many nights should the star be observed? It depends on the rotation rate of the star. Some stars have rotation rates on the order of days, some on the order of weeks, and some of them have very unknown rotation rates. So a good rule of thumb is just if the star is up and you have a few extra minutes, just observe it for 15, 20, 30 minutes and get some data and submit that to the AVSO's variable star catalog. And you can contribute data that way as well. Gary, I think I answered this a little bit earlier, but if you search for the Pandora mission website, those 20 plus planets are published on the website as well. And then Sam is asking, could you elaborate on how transit time refinement enables us to save minutes or seconds on large telescope scheduling? So I kind of glossed over this really quickly, but basically, if there is a 5, 10, 15-minute uncertainty of when the next transit were to occur, that is an extra 5, 10, or 15 minutes of overhead that I need to build into my observing campaign. So I might write a proposal for James Webb and say, hey, I want to observe this transit, but I don't know exactly when it'll happen. There's a 15-minute uncertainty, so I'm going to ask for an extra 15 minutes of overhead just to be safe, to make sure I get it. 15 minutes here or there is not a big deal typically, but if you start looking at tens, hundreds, or thousands of planets like Ariel does, this can result in many, not only hours of wasted time, but days of wasted time waiting for these transits to occur. But if we can observe these transits ahead of time from the ground and more accurately measure when these transits are occurring, that will give us data that's more recent that allow us to more accurately predict when the next transit event were to occur. And therefore, we can more accurately predict when that happens and observe them more efficiently with James Webb and Hubble. Next question is, what mechanisms are in place for scaling this globally for citizen science, especially from underrepresented regions from different light pollution equipment access levels? So a variety of different ways. We actually have, for example, in Africa, EPAC's lab, they're participating in Exoplanet Watch. They actually wrote their own proposal to get data from Las Cumbres Observatory to use their robotic telescopes. But they also use data from us, from the Micro Observatory. And that's one of the reasons why you can actually just use your smartphone, is we wanted to make sure that you didn't have to have a nice MacBook Pro or a nice supercomputer to participate in this program, or even access to a telescope. As long as you have at least a smartphone or a Chromebook, you can then check out data from us and analyze this data and then contribute it to us as a full participant. The next question is, are folks using AI and ML, so artificial intelligence and machine learning, to look at the data from Pandora, Hubble, and James Webb? Yes, people are using AI and ML methods to stitch together data, to analyze the atmospheric signals, but there still, as far as we can tell, requires a human in the loop to do the data analysis. You still need someone to keep their finger on the pulse, or finger on the scale, really, to make sure that things are not going wonky. All right, getting to the last three questions here. Pat's asking, should observation data for Pandora be submitted to the AVSO exoplanet database? Yes. But for the outer transit observations, you submit that to the variable star catalog. And I'm probably messing up that name, Bert. What's the correct name of the AVSO variable star catalog?
It's the AVSO International Database, or AID. It's our standard photometric catalog.
AID, that is it. Sorry, always messed it up. So the AID is where you contribute the star alone measurements of the stars. So Pat, if you use Exotic actually, and you observe a full transit, Exotic will actually automatically not only give you the transit measurements you upload to the ETD, it'll also use the out of transit portion, with the planets not blocking the star, to give you the stellar variability measurements. And then that you upload separately to the AID. So basically, by observing a transiting exoplanet, you get a twofer. You can observe a planet, and you also observe its host star. And Sam, exactly. That is why you need the data observing the surrounding the transits as well. This enables us to observe the baseline, to calibrate our data analysis method. It also helps us observe the star effectively free, which helps us then to quantify its activity and helps us remove that from the planet as well. Horace is asking, would it be possible to look for Zeeman splitting to distinguish between star spots and exoplanet transits? Of course. The only problem is you need very high spectral resolution, a resolution of many thousands. And sometimes you need large telescopes, 4 meters or larger, to observe Zeeman splitting. Unfortunately, those telescopes are also wanting to be used by many people across the community and the world. So their time is very limited and very competitive as well. So we have to be realistic. We need to observe hundreds, if not 1,000 planets and their host stars. And we think we can do this with photometry. And this is exactly where you can come in and help out as well. All right, so I think I went through all of the open questions. There we go.
Yeah, you got them all done, Rob. Thank you very much.
Nice.
Wonderful. So, all right, well, we'll go ahead and do kind of the outro here. So, Rob, I'm going to steal the screen from you. All right. Well, so I'd just like to say thank you, once again to Rob and Rob. Like, our collaboration between AVSO and Exoplanet Watch has been incredibly wonderful. And you jest that we keep bringing you back. Well, the answer is, you guys are doing really great work, and we really appreciate the collaboration. So, please, for those of you that are interested in observing exoplanets, go check out Exoplanet Watch and try to get involved. You can do some really interesting and incredibly useful science with relatively modest means, and they're also making making it so that people worldwide can use something that's as simple as a smartphone to go out and reduce the data. Not a lot of citizen science organizations are capable of doing that. So I'd also like to issue a special thanks to Boyce Astro, who has actually sponsored this series in whole. And so, as you know, Boyce Astro, they provide online astronomy education, observatory resources, and research experiences for students and astronomy educators. So if you could please go check them out over at boyceastro.org, I'm sure they would appreciate it very much. And of course, the AVSO is going to have, we're continuing our webinar series for the rest of the year. So we're going to enter into one of our special interest group webinars. So if you recall, AVSO usually does summer section webinars. This year, we've decided to split them up over the course of the entire year. And so at our next webinar, which will be coming up June 7th, we're going to be talking about our exoplanet sections, our solar section, as well as our young stellar object section. So be sure to go ahead and register for that. You can use the QR code right on the right-hand side of the screen, or you can go to avso.org/webinars and learn a little bit more. And of course, for those of you that are attending, if you'd like to rewatch any portion of this webinar, or if you'd like to share this with any of your friends, we will post the webinar over to our YouTube channel, which is AVSO HQ on YouTube, probably within the next few days. Usually about midweek, it ends up online. So we'd really appreciate it if you were to, subscribe to our channel as well as share your videos with your friends. And when you leave the webinar today, you will also be presented with a survey. At the end of the year, we end up looking at the results of all these surveys, and it helps us decide the kind of content we're going to be providing throughout the rest of the year. And any information that you can give us, things that you like, things that you don't like, things that you'd like to see more, help us pick webinars that are actually going to be really interesting for you. And so I'd like to just one more time thank Dr. Rob Zellam for spending his Saturday with us. And Rob, it's always a pleasure having you here. And, we look forward to continuing our collaboration with Exoplanet Watch.
Yeah, thanks again for having me. And thanks again to everyone across the globe for calling in, and appreciate it as much. And hopefully see you on the Exoplanet Watch Slack or participating and contributing to Pandora. Thank you again, AVSO, for having me. Always a pleasure, as always. Lots of great questions. And have a great rest of your day, and happy Star Wars Day Eve. So make sure you go celebrate Star Wars Day, May 4th.
Yeah, make sure you have all your Star Wars puns ready for tomorrow.
May the 4th be with you.
Indeed. All right. Well, we'll see you all later. Take care. Bye-bye.